Okay, cool. I would love to introduce Dr. Jeffrey Siegel. Meeting all kinds of cool people today. It's great for me, and I'm sure all of you. Dr. Siegel is a professor at the University of Toronto in civil and mineral engineering. Interesting department there. And he's also a chair, the so-called Baden-Tannenbaum chair. That's obviously a honorific, prestigious in civil engineering. And he also has an appointment at the Dalalana School of Public Health, so that's a great connection to us. He researches healthy and sustainability in buildings, filtration, air cleaning, etc., many of the things you've heard about. Where is Jeffrey, actually? Okay, no, it's okay. Your picture looks like you're about 20 years old, and I was thinking about how many papers you've published in your 20 years, but maybe you're late 20s by now. Anyway, congratulations on that, and also applying it to COVID-19, which is obviously important. And I will say, which is probably clear to everyone, the aerosol-related people have done such a tremendous job for the community by applying their skill set to COVID-19. So thank you, Jeffrey, and take it away.
So thanks very much for the invitation to be here and for the introduction. I'll begin by acknowledging I did not get the memo about the Rolling Stones titles, but this is in fact the title of one of their very early albums. You probably don't know it. So I'm going to start with an email I received last week from, this is part of it, from someone in Kamloops, and I don't want you to read the whole thing. I'll return back to this email at the end of the presentation, but there's just one point I want you to get from this, and that is that people really are horribly impacted by extreme heat and wildfire events, and very often reach out to strangers on the internet. So we all get lots of emails like this. And this is I'm going to talk a lot about the details of filtration and ventilation systems, but this is really about real people and how they're impacted and what can be done about that. The kind of central issue here is that we have a lot of great strategies out there to make buildings resilient to extreme heat and to smoke events. And I'm going to argue today that a lot of the challenge that we face is not so much in knowing what to do, but knowing how to do it and how to do it well in the large number of buildings we have to do it in. And as just one example of that, this is a document that's gone through several iterations. It originated, I think, about 40 years ago or so from the US EPA, and it talks about what to do for wildfire smoke. And the exact same things that are in this document are exactly what I'm going to talk about today. So it's not like adding new knowledge, but I think there's a real kind of implementation piece that's very important. I think everyone has a basic sense of what heating, ventilation, and air conditioning systems are. They do a lot of different things for us. A lot of people kind of talk about them as the lungs of the building. This is one example, a figure that Elliot showed as well, of a commercial forced air system. I'll modify it and make it residential in a second. But there's a lot of components there, and there's a lot of things that aren't well reflected in the picture. There's complicated distribution systems. There's a ton of controls. We're all used to things like thermostats, but there's a ton of other controls in the system as well. And we all have this view of the HVAC systems in the buildings we inhabit. But in reality, there's this enormous diversity and this enormous amount of dynamic behavior with HVAC systems. And so I think the idealized view we might have in our mind is HVAC systems are all about comfort, maintaining indoor air quality, thinking about energy efficiency. And I don't want to go too far with this, but that's kind of not right. The reality is HVAC systems in general, and I know there are some great HVAC systems out there, are kind of more marginal in their operation a lot of the time. And I think it's really important to bring up this point right now because, in many of the things I'm going to talk about today, we want to push our systems and our buildings to do things to help us be more resilient. And we fundamentally have some challenges we're going to have to address in a lot of buildings before we do that. One of the things I want to do when talking about HVAC systems, because it's important before I leave this slide, is kind of talk about what the differences are between that kind of idealized commercial forced air system and what we see in some residences. And by and large, what we see, and there's a really important difference here that's going to kind of underlie some things I'm about to say, is that a lot of our forced air systems are what's called recirculating. They don't have any connection to the outside. So the thermostat calls for heating or for air conditioning, depending on what the system is equipped with, and the fan comes on and cold or hot air comes into your building. And that really is going to determine a lot of what we're able to do under more extreme circumstances. Just to make this point kind of crystal clear, this is a series of figures I stole from an NRC publication, and nothing depicted on this page is ventilation, right? So the first figure is showing the impact of leakage. So there are holes in the building enclosure, and depending on a variety of factors, air will flow in and out through those holes. There is a recirculating forced air system in the second picture that distributes air, conditioned air throughout the building, but it doesn't necessarily, in fact, it usually doesn't have a connection to the outside. And then there's lots of air movement within buildings caused by things like fans and temperature differences and a variety of other things. And that's air moving around in the building, often in a relatively uncontrolled manner. And that's not ventilation either. And so when we're thinking about wildfire smoke, or even more broadly than that, there are kind of two terms that I think are very important. One of them is ventilation. And ventilation means fresh air from outside. Now, that gets a little bit complicated because if air is not fresh, because, for example, there's a wildfire plume or something else outside, ambient air pollution, you have to filter that air in order to make ventilation beneficial. And then there's also, kind of related to that, this concept of filtration, which I'm going to use in this talk to mean air that is recirculated through something that removes particles generally. As Elliot mentioned, you can remove some amount of gases depending on what they are with some filters as well. And filtration can, of course, be central, like in the systems I just showed you, or it can be portable systems as well. And just to kind of calibrate your expectations here, I don't have BC-specific numbers, but for Canada as a whole, about 55% of homes have forced air systems that provide either heating or cooling or both. So there's a lot of homes that can't benefit from forced air systems, at least as they are now. Around less than 10% of homes have a connection to outdoor air in their ventilation system, a dedicated mechanical ventilation system. And, when talking about these things, and I'll talk about this a bunch, we can't just talk about what they do for the things we want them to do. There are, of course, energy, noise, cost, other consequences, too, that are really important. So what we often talk about with ventilation, especially from the perspective of wildfire smoke, is we want to positively pressurize the building with filtered outdoor air. And so the idea here is you bring in air from outdoors, you filter to clean it of what's in the air, and then you are supplying more air than you are returning, and so the building is positively pressurized. And that's a great vision, but the reality is that, first of all, as I already said, a small number of homes have the capacity to do this. And in terms of cleaning the air, again, we can remove the particles with a good enough filter if it's done well. But some of the other constituents of wildfire smoke are quite challenging to deal with. There are, of course, energy consequences. And, a lot of our building enclosures, what's often called the envelope of the building, is not tight enough to allow for consistent, high-quality, positive pressurization. So the analogy I always think about is we're trying to inflate a leaky balloon. In order to do that, you have to put in so much air that the energy consequences, as well as just kind of raw system limitations, can you get a fan big enough? That's the issue. And so the reason I bring that up is that, this is a great vision, and it's something that we can certainly do with newer homes. It's just more of a challenge in a retrofit because you're not just talking about the system, you're talking about the bigger building and the building enclosure. If we want to talk about filtration, and filtration as an approach for removing particles from wildfire smoke or anything else, I kind of divide that in my mind into 3 bins. You have to get the air containing the particles to the filter, and that has to happen before someone is exposed to it. That filter has to actually remove the things from smoke that you want it to remove, and that removal has to be important in the overall context of the building. So I'm going to talk about each of those in turn, just to give a context here. So this is a plot of something called the runtime, which is on the y-axis, which is the fraction of time that the fan operates in a forced air system. These data represent monthly average data for a year from about 6,000 homes in North America, including a reasonable contribution from homes in BC. And what's on the x-axis here is the outdoor temperature. And there are 2 things I want you to get from this picture. The first one is there's enormous variation. Some homes, at some times, the fans run barely at all. Other times, some homes, the fans run a lot of the time. Well, that's really important from the perspective of a filter, because if there is a filter in that system, it obviously doesn't work when no air is going through it. The second comment is the red dashed line there is the median across this entire sample of homes. And the median is about 18% or so. And so that means that over 80% of the time in a typical North American residence, air is not going through the filter. So we can't just talk about the filter, we also have to talk about issues like this, the fan. If we move on to the filter itself, you may or may not be familiar with filter efficiency curves. One example is shown here for quite a good filter. Filter efficiency curves as a function of particle diameter, which is what's on the x-axis here, are U-shaped, meaning small particles are easier to remove because of Brownian diffusion. Larger particles you can remove because of inertial mechanisms like impaction. And it's the size in between, usually about kind of 0.1 to 0.3 microns, that's the hardest to remove. And that's really important from something like a wildfire smoke perspective because there's a lot of those kind of harder to remove particles in the mix. So all filters will have an efficiency curve that looks like this at some level. And what we're basically talking about is how deep that U goes or how low the efficiency goes in that U. And so there's many different ways of classifying filters. This is the main data table from ASHRAE standard 52.2. And if you've heard of MERV values before, this is where they come from. So a filter is tested in a laboratory, and depending on its efficiency, it gets a MERV. The bigger the MERV, the more efficient the filter is. So that's kind of the very straightforward view of filter efficiency. The reality in real buildings and real homes is much more complicated. So this is some data from 20 homes in Toronto, all installed with a brand new MERV 14, so quite a high efficiency filter. You can barely see it, but there's a black line towards the upper right of the plot. That is the efficiency curve from the standardized test from that ASHRAE standard 52.2. All of the symbols, one symbol per home, represent the actual efficiency of the filter as we measured it installed in the system. And while a few homes are near what the standard says the efficiency is going to be, a lot are not. A lot are much lower, and some are much, much lower. And so there is this big difference between filter efficiency as it's labeled, tested in a laboratory, and what we get in real homes. And there's a lot of reasons for this, phase velocity and other things. And one of the big ones is this practical issue of bypass. So a lot of our filters aren't installed with gasketing. Some of them have quite large gaps around them. And of course, air goes through air goes around rather than through the filter. And so it's really important that we not just talk about the filter, but the broader context of how it's installed. And one more piece that makes it even more interesting is that some filters decline in performance as they age. This figure is from a filter in Finland. These were the researchers who kind of first did the research on this effect. And you can see that the filter started out quite a good filter, those black squares at the top. And after 9 months, this filter was rated for a year of lifetime. You can see that its efficiency has dropped quite dramatically, those white triangles at the bottom. And so filters decline in performance, and it depends on what and how much filters are loaded with, as well as some environmental factors like relative humidity. But again, in a practical sense, this is from that same study I showed you. Each of these pairs of bars represent the 20 homes. The lighter colored bars when the filter is brand new. The darker color bars after 3 months at the end of the filter's life. And all of the filters that have an E after their MERV are what's called electret filters, or these charged media filters. And you can see that they all have declined in performance as they age. And the one filter that was the lowest efficiency filter, the MERV 8 filter, did not decline in efficiency because it's not this charged media type of filter. And so, it's really important, again, that we don't just take a filter efficiency rating or output from a standardized test and think we're going to get that. One final point on the kind of contextual issues of filtration here. This is a measure, this is a plot that represents a bunch of different studies in the literature that all measured something called effectiveness. And they all had different methodologies and so on. But the big picture I want you to get from this is that just because you have a high efficiency filter, you don't necessarily have high filtration performance, because it depends on all of these contextual factors. And so when we're thinking about telling people to use filters to protect themselves, we have to do more than just specify a filter. To summarize everything I just said in the last few minutes, install a good filter properly, use it well, make sure lots of air goes through it, and especially after something like a wildfire event, change it. There's a lot more I would say, but I'm not going to in the interest of time. I just want to make one point. Especially in a lot of newer homes, we tend to locate ducts outside of the conditioned space for aesthetic or space reasons. And so if we think about, well, why don't I just run that fan all the time to get the benefit of filtration? You have to be a little bit careful with that because of the distribution system, the duct system that I mentioned. If that's outside of the conditioned space, and all duct systems leak, some of them quite a lot, you can end up changing the pressurization of the home, as well as kind of bypassing the filter with that leakage. So again, this is a system problem. This is a building problem, not a filter problem. The summary here is, not every home can use these strategies. First of all, not every home has a forced air system, and certainly not every home has mechanical ventilation. So we have to think about how we're going to retrofit lots of existing homes to do this. And, there is this real piece about doing it well. It's insufficient just to do it because of all the issues that I just mentioned. I want to talk about portable filters as well, because portable filters are the solution that, kind of what you need for them to work is money to buy a filter and electricity. And there's lots of different portable filters out there. We care about their cleaning power, which is reflected in the clean air delivery rate. The higher the clean air delivery rate, the better the filter will clean the air of wildfire smoke or other things as well. And, there's lots of different types of portable air cleaners. Fundamentally, as I say, we care about the clean air delivery rate. You will hear consistently that noise is a concern. So a big portable air cleaner is going to be loud, and so there's a user expectation piece to manage there. The cost issues are large, and you might have seen some of the kind of do-it-yourself filters that have been out there for wildfire smoke protection, as well as now for COVID. And they've gotten kind of increasingly sophisticated. And they partially address the cost issue, although they still obviously take both the cost and the electricity to run them. In general, these things target particles, which are an important component of the health effects we see, but they're not the only thing. There are some modifications you can get. Again, it's a question of money generally and availability. And Elliot already mentioned this, but there's a lot of unproven technologies out there, ionization and other things that you should steer clear of. I've talked a lot about wildfire smoke, and I wanted to just talk a tiny bit about extreme heat. Obviously, HVAC has a huge role in protecting from extreme heat. And we have a bunch of different tools in the toolbox that are very kind of building specific. You can add or enhance kind of conventional compressor-based or mechanical cooling. And the important thing here is that there are always kind of counterbalancing issues that we have to consider. So, for example, obviously air conditioners can use a lot of electricity. Electricity can, it's not just important the amount of electricity we use, but when we use it, because of demand issues and what generation resources are needed to provide that electricity. In some climates, including some climates in BC, you can use evaporative cooling, which is a lot more energy efficient. There can be maintenance and other issues that accrue. We can also shift the time in which we use cooling. If we have thermal mass available, we can kind of cool down ahead of time to avoid needing to use air conditioning during peak periods. Again, this depends a lot on having a building that's designed to do this well. And of course, this isn't an HVAC measure, but it's worth mentioning that the direction we really need to move in for the climate change implication reasons is avoiding the need for cooling whenever possible. And that has to do with how we design our buildings, and that's something that we definitely need to aggressively move towards. So, how do we optimize all of this? There's been some discussion already, and I hope there's more. People need guidance. And it's not just a question of making guidance available. It's looking at how to make guidance effective. And I think in the indoor air quality community, we haven't done a great job of looking at that question of effectiveness. And how can we message a lot of the measures we need to get to people? There is a discussion that I wrestle with a lot, but I think is also really important, that we have a housing quality problem in a lot of parts of Canada. And so, again, we have, HVAC systems or building enclosures that don't allow us the flexibility to provide resilience. And so we have to think about how we're going to address that. And, of course, it ties in very closely with the, housing availability issue that pervades a lot of Canada as well. And there's some balance there. And then we have this kind of plethora of low-cost sensors available to us now and that measure things like particle concentrations or CO2. And I think that gives us some opportunities for things like automated control, predictive behavior. I'll give just one example of that. This is some data from social housing apartments in Toronto. Basically, we had about 75 different apartments in a study. And in this work, this is modeling work done by Alex Mandel, a graduate student, we're looking at the question of, could we optimize how those systems perform and make them tailored to the individual apartment that they were in? So someone who has a strong particle source in general in their unit is going to get a different benefit from filtration than someone who doesn't, or when there's a wildfire plume event. And so this is essentially using machine learning and sensor outputs to say, hey, can we improve the energy efficiency or improve the amount of benefit we get per unit of energy input? And the answer is yes, we can do that substantially. And I would further add to this that there is an interaction that was, I think, mentioned by Elliot about the electrical grid and things like wildfire and extreme heat events. And so this type of approach can also be used if we're powering systems on batteries to make things operate much better. And of course, in the short term, community cooling centers and safe zones are obviously going to be a part of our future because we do have this massive housing stock that we're going to have to address, which isn't going to happen overnight. So I want to return back to this email that I started with. They live in a multifamily building, and their landlord provided a through-the-wall air conditioner that's really, really loud and hard for them to use. Because of the noise, it's probably also, knowing how most of these systems are installed, allowing a fair amount of air leakage, which has that interaction with wildfire smoke. Their landlord also provided them with a portable air filter, which is a decent portable air filter. It's a little bit undersized for their apartment. But assuming they're changing the filters and so on, it's certainly a lot better than not being present. But the point I make here is, they had a landlord who could take these measures, and they're still searching for solutions to make their situation better. And so I think it's important to kind of acknowledge we have answers, but we have to go further and make sure those answers are actually working. So to kind of wrap up here, we have, I think, implementation issues much more than we have technical issues. And the point that Elliot mentioned, and I know there's going to be a much more formal treatment later today, that's really important to keep in mind is that, we do have systematic health disparities across Canadian society. And I think that we should take this opportunity to address housing quality to start partially addressing some of those equity issues. And, I think that we should be targeting our resilience measures to where they are going to most beneficially affect, the kind of most marginalized and racialized parts of our populations. So I'll finish there and be glad to take any questions. That's right.
Jeff, do you see a increase in residential systems using dedicated outside air systems?
Certainly, yes, is the short answer. But where I see it most commonly is in new homes and in major retrofits. And, that tends to skew some of the disparities even further. And so we don't really have good low-cost ways of getting mechanical ventilation, or we haven't really done that as much as we should in existing homes.
Well, Adams. No, it's okay. Come on up. And I'll just quick question. With the technology you were alluding to, I don't think you used the word electrostatic, but I'm sure you're aware. Would you caution with electrostatic in addition to what you said about the gaseous emissions that come from them?
Yeah, okay. So, I should have been a little more careful with my terminology. So, electret filters, the kind that I talked about, the decline in performance, they are charged at the factory. They don't emit anything. They just maybe don't work as well when they're old as when they're new. There's another class of air cleaner called an electrostatic air cleaner, which is actively using electricity to charge particles and remove them. The kind of devil is in the details here, but certainly some electrostatic air cleaners have been shown to emit ozone, which is a respiratory irritant and a hazard and something we don't want in our buildings, and can lead to a variety of other things that are of concern. So this is kind of a bland answer that will potentially get me in trouble, but I would say stick to what we know works, which is media filtration and supplemented with things like activated carbon, and other proven technologies. Avoid things that might be causing more harm.
Thanks, Dr. Siegel. This is me asking a question that selfishly helps me prepare for my talk later. With regards to guidance, what would be your perspective on whether we've spoken enough about natural ventilation, either pro or against, but in terms of the thoroughness of that part of ventilation?
Yeah, so, I'm married to an architect, and so I always have to be careful about how I talk about open windows and so on. But I am a firm believer in, I think the pandemic has shown us how important it is to be able to open windows and to even more sophisticated natural ventilation systems. I think that the cautionary note is that people need more information than they currently have about how to operate those systems well. This whole idea of when it's a little smoky outside, yeah, it's probably okay to open my windows, is not particularly good guidance. And so people need both good information and effectively messaged information to be able to operate those systems well.
Hi. Yeah, so there seems to be a bit of a trend with furnace installers for forced air systems to use lower MERV filters. So I've always asked this question to them, whether it's for natural gas or heat pumps, and they say the higher MERV filters make the system run harder, and it's hard on the system, so to not use them. So I'm just wondering if you could speak to that.
So this is one of the things that I could talk for another hour about, but I won't. The short answer is absolutely there can be an issue. A higher efficiency filter often, but not always, has a higher pressure drop. But that is a relatively straightforward problem to solve. The reason that an installer wants to put in a low efficiency filter is they don't want to have to deal with any of that complexity, right? Anytime they get a callback or something like that, that's kind of lost revenue. And so we need to shift the HVAC industry to be able to use better filters and not have the default like, oh, I don't want to try that because that might cause a problem, but also to use them well. So the story I always tell is when I lived in Texas, my house there, I wanted to get a better filter installed. And the HVAC tech was like, it's really I don't want to do that for the exact reason that you mentioned. And the short answer was, at the end of the day, I think it was $75 to put in a gasketed, beautiful filter slot that could take high-efficiency filters and work wonderfully. And so, again, not everyone has $75, but it was a silly reason to not just say that at the start and then get it done. And so I think that barrier is there, but that's more an education barrier than anything else.
Cool. Okay. So thank you. Now this one for some reason has this cute little picture that I guess tells me what's in there, and it looks quite beautiful.
Okay. Awesome.
So thank you. Again, thank you very much.